In digital communication laboratory, we study the following three experiments: ASK, FSK, and PSK. Our aim is to generate and detect ASK waveform using SL100 transistor. Here is the definition of ASK. What is ASK? Amplitude shift keying. So in digital communication, we transmit binary 1 and binary 0. So to represent 1, we are transmitting carrier, and to represent 0, we are not transmitting carrier. So this kind of transmitting the carrier when binary 1 is to be transmitted, that is ASK, amplitude shift keying, also called as on-off keying. Circuit diagram for ASK is as shown. This is ASK wave generator. The second part is detector. The third part is the wave generator, that is message signal generator. To design this circuit, let us consider the following parameter, that is VC peak at this point, that is collector is 2.3 volts, and VBE is 0.7 volts and VCE is 0.3 volt. And let us consider collector current is 2 milliampere. So writing Kirchhoff voltage law for this outer loop. So we get VC peak minus VC sat minus IRE, that is equal to 0. Solve this equation, you will get 1 kilo ohm. RE is 1 kilo ohm. To find the value of RB, let us consider the peak voltage of this message signal is 4.7 volt. So VB here is zero point 0.7 volt. So write equation for this inner loop: VB minus IBRB minus VBE minus VE, that is equal to 0. Since IC is equal to IE here, the value of VE is nothing but IE into RE. RE is 1K, so IC is equal to IE, that is nothing but 2 milliampere. Therefore, VE we get 2 volts here. We also know IC is equal to beta times IB. So since IC is 2 milliampere and beta is 100, therefore the value of base current that we can expect here is 0.02 milliampere. So substitute all these value in this equation, we'll get the value of RB approximately 10 kilo ohm. So now how to find the value of RC, that is timing element that we connect after the detector diode. So this is the time constraint we have to consider. Timing constant must be greater than 1 by Fc, less than 1 by Fm. That is nothing but, what is Fc? It is nothing but carrier frequency. What is 1 by Fc? It is 1 millisecond. What is Fm? That is message signal frequency, that is 10 millisecond. So you substitute the value of C by assuming it as 0.1 microfarad, and we get the value of RL to be connected here. In order to avoid single strand wire, connect the component on the breadboard like this. So insert op amp to the zip socket and lock it. Now you connect collector of the transistor to one of this point on the springboard. Connect base of the transistor via 10K, and here you are applying message signal. Connect emitter of the transistor here and connect 1K resistor ohm. Consider this as your common ground. So this is where you are going to get ASK output when you turn on the signal generator. You apply collect, that is carrier signal here and message signal here. So in the second part, you are connecting diode directly to pin number 3 of op amp. Across that, you are connecting the capacitor and resistor 10K, and it is connected to common ground here. In order to power up the op amp, you are connecting fourth pin to minus VE and seventh pin to plus VCC, and you are taking the output at 6 by connecting a V reference to pin number 2 of op amp as shown. So this is the circuit connection. When I connect all the cables, that is 3 cables from the power supply to power up the op amp, and 2 signal, that is 1 carrier signal and 1 message signal, and 2 CRO cable that you can see here, M of T and the output of T at pin number 6. When you turn on, you are able to see here the waveform, that is the output waveform. So this is nothing but our TB duration. Binary 1 is for 5 millisecond and binary 0 is for 5 millisecond. There are 5 cycles of carrier that is present in 5 millisecond that you have to note. Whenever 0 is transmitting, we are not transmitting any carrier signal. Similarly, when you connect the op amp output at 6, you are able to see the waveform that is looking like this. So this is nothing but our input wave and this is output wave. So here you are able to see, you have to measure T on of this output wave. This is T on, and total T you have to measure. You have to find the duty cycle. You have to find the duty cycle on this wave. So how to find? So T on you have to measure and T you have to measure for this wave. So duty cycle is nothing but T on by T. So what is the duty cycle of the message signal you are applying? That is 50%. 50 minus duty cycle, take this, that is your error rate. That is your error rate. What is the frequency of the message signal? You just note it down by this expression, frequency, that is equal to 1 by T. So this is the analysis of output. Here you are going to see 1 kilohertz sine wave and 100 hertz square signal that is applied. So this is the waveform that you have to write after conducting the experiment. So for binary 1 is transmitted for 5 millisecond, 0 is transmitted for 5 milliseconds. So total duration is 10 millisecond, and this is the carrier that is we are using. So whenever binary 1 is transmitted, 5 cycles you are able to see, and here the demodulated wave you can see here. So the next experiment is FSK generation using SL100 and SK100 transistor. So what is frequency shift keying? It is nothing but transmitting two frequencies to represent binary 1 and binary 0. So here binary 1 is transmitted by using high frequency carrier, and binary 0 is represented by transmitting a low frequency sinusoidal signal. So the circuit diagram is as shown. This part of the circuit represent FSK generation, and this part represent the diode detection, and this part represent the message demodulation. The design equations are same for all the three circuits. It is the analysis of circuit is very simple. Whenever base voltage is positive, the upper transistor is turned on. So at this point we are going to get the high frequency carrier. So whenever base voltage is 0, lower transistor is on and upper transistor is off. Therefore, we are going to get the low frequency signal here. So continuously the transistor are turning on, turning off depending on the base voltage. So that waveforms are applied to diode detector. Positive half cycles are available at the output of diode detector, and the capacitor charges to the peak of positive half cycle, and that is applied to pin number 3, that is non-inverting terminal of op amp. And here we have applied a reference voltage to pin number 2 of the op amp. So here the op amp always oscillate between plus V saturation to minus V saturation depending on the difference between the voltage. So in order to avoid the single strand wire, you can connect the circuit connection on springboard like this. So first connect the base resistance, that is 10K and 10K here. Connect the emitter resistance 1K and 1K here. Now you connect SL100 emitter 1 to this point and SK100 emitter 2 to this point. You connect SL100 base here and collector you connect to this spring point to apply carrier frequency 1. Similarly, you connect collector of second transistor to this point to apply carrier frequency 2 from the signal generator. Connect base of second transistor to this point. Now you apply M of t to this point. Now you are short circuiting the two emitters and you will get the FSK waveform at this point emitter either here or here. In order to demodulate and generate the binary waveform, you connect directly the diode from one of the emitter to pin number 3 of op amp. Refer circuit diagram. I am here eliminating the use of single strand wire. Too many single strand wire don't use. Now you connect R and C component to the common ground like this. So apply reference voltage to pin number 2 and apply the biasing voltage to op amp plus VCC to 7 and minus VE to 4th pin, and you observe output at pin number 6. You are able to see the output after connecting the cables like this. So this is our FSK output for binary 1 high frequency and for binary 0 low frequency, followed by the decoding, that is demodulation. You can able to see here, this is the input wave and this is the message recovered. As usual, you measure on time of this and total T, find out the duty cycle and find out the error and find out the frequency of the message signal recovered. So this is the waveform that you can write for the frequency shift keying. In a similar way, we can generate PSK, phase shift keying. What is phase shift keying? It is nothing but to represent binary 1, we are transmitting in phase carrier, and to represent 0, we are transmitting out of phase signal. You are going to see continuously presence of W and M in the waveform that is generated. That is called phase shift keying. Circuit connection in order to avoid single strand wire. So this is the circuit that you can rig up on the springboard. Here I have placed SL100 and here SK100. I have connected here 10K resistor and I connected base of the transistor to the two ends of the resistor, and here I am going to apply the message signal, that is square. Now I am going to connect emitter of two transistor to these 1K resistor, and this terminal will be the common ground. In order to avoid multiple single strand wire, I directly connect 10K to pin number 2 of the op amp, and pin number 2 to 6 I have connected one 10K here. So now pin number 3 I am going to connect, pin number 3 I am going to connect to this emitter, that is 10K, and from pin number 3 one 10K resistance connected to ground. So this is the simple connection. So when you connect all the CRO cables to common ground and op amp power supply, you are able to see the circuit like this. So when you power up, you are able to see the waveform, that is this waveform. Whenever you are able to see 1 to 0, 0 to 1 change, you are able to observe here there is a phase shift here. So in the same way, you are going to see the message signal that is recovered when you connect the demodulator or detector circuit. This is nothing but T on off recovered signal, and this is total T, that is nothing but 10 millisecond. Find out the error between these two and find out the message signal frequency. So here you can write the result of the experiment you obtained. That's all about the three experiment in digital communication: ASK, FSK and PSK using transistors and op amp.